Hello and welcome back. We're now going to talk about refraction of light, which is the bending of light when it goes from one medium to another. So if you put a straw in a glass of water or put a spoon, you'll see that it looks bent when you look at it through water versus through air. And so that's the property we're going to discuss. That'll lead us to Snell's law of refraction. And we will also talk about total internal reflection, which happens in certain conditions when refraction is impossible. So if I have a slab of glass that's lying on a table, and let's say I take a laser pointer and shoot a ray of light at an angle at it like this. From practical experiments, we know that when the ray of light reaches glass, it's not going to continue straight, it's going to bend this way. And then when it comes back out of the glass into air again, it's going to bend this way again. Here, the index of refraction of air is over here. The index of refraction of glass is over here. And for light to bend like this, N1 will be less than N2. So it bends closer to the normal when you go to a medium with a higher index of refraction, and it bends away from the normal when you go to a medium of lower index of refraction. So let's set that up here. I'm going to draw a normal line to the glass in both of these places, and here is theta I, the incident angle. Here is theta R. In this case, theta R stands for the refracted angle, not the reflected angle as before. And then in the transition from N2 back to N1, you could consider this here as theta I and this as theta R, the refracted angle. Since the I and R subscripts there are a little bit confusing, I'm just going to change these to numbers. So let me just now say this is theta 1, the angle of the light ray from the normal in the medium where the index of refraction is N1. Then it goes to theta 2. This is also theta 2 because these two normal lines are parallel to each other. And then this will become theta 1. So listing these properties, let's capture the main point. A ray of light bends when it goes from one end to a different end. So when it goes from one material to another material where the index of refractions are different, the light ray bends. And the way it bends is it bends towards the normal if N2 is greater than N1, and it bends away from the normal if N2 is less than N1. So in this first transition, when I'm going from air to glass, glass has a higher index of refraction than air, so it bends towards the normal. And when it goes back from glass to air, air has a lower index of refraction than glass, so it'll bend away from the normal. How do we explain this? I'm going to try to explain this in two different ways. First, I'm going to take this boundary between air and glass. So here I got N1, here I got N2. N1 again is less than N2. And I'm going to take a wave front, so a beam of light with a wave front like this. So let's say these lines across the beam represent the crests of waves, for example. So they will be marching on like this. As the ray of light goes in air, they will be equally spaced because the speed of light is constant through air. Now, from the previous video, you know that when light goes from air to glass, it slows down inside glass. And that was given based on our previous video. So I had V1 was C divided by N1. And if I have V2, it'll be C divided by N2. If you divide both these equations, you will get V1 over V2 equals C over N1 divided by C over N2. This will be C over N1 times N2 over C multiplied by the reciprocal. The C's will cancel. So V1 over V2 will be equal to N2 over N1. And since N2 is larger than N1, V1 will be greater than V2. So light will slow down inside glass. So it's going to go slower, which means this end of the beam, which entered the glass first, is going to slow down. And this end of the beam that's still going in air is going to continue to be going at a faster speed. So as a result of that, what ends up happening is this ray of light bends toward the normal like that. So by going slower, it'll automatically have to bend. That's one way to understand this. The other way to understand this is to think about a property of light that if it needs to go from point 1 to point 2 and it's going through, let's say, just air, for example. So let's say it needs to go to this point 3 first, 1 to 3. Light is going to follow always the path that'll get it quickest from point A to point B. So in this case, the path that'll get it quickest from 1 to 3 will be the straight line that connects 1 and 3. So light in general travels in a straight line, which is why we use that ray model. But if it needs to go from 1 to 2, N2, where it's going to go faster in air and slower through the glass, this straight path turns out is not the quickest path, because the straight path is going to have it going a certain distance through air and this distance through glass, and let's say these two distances are equal. That's not the fastest. In order to go the fastest route, you're going to have to find a path that goes longer in the medium where you can go faster and a shorter distance in the medium where you go slower. So it will not go in a straight line between 1 and 2. That won't be the quickest route. Something like this will be the quickest route. So it'll end up taking this path and hence bend. So those are my two reasons for why you can think of light ray bending. And based on the mathematics behind taking the shortest duration of time, we end up with something called the Snell's law that defines how it bends. Snell's law tells us that n1 sine theta 1 equals n2 times sine theta 2. Once again, these angles are measured with respect to the normal. And even from this relationship, you see that if, like in our example, n1 is smaller than n2, sine theta 1 would have to be greater than sine theta 2. And the relationship between sine and theta is directly proportional, so theta 1 will be greater than theta 2, which means it'll bend towards normal. So all of that is consistent with our statement over here. All right, the last thing I'm going to talk about is something called total internal reflection. So this happens only when you go from a medium that's a higher index of refraction to a medium that's lower index of refraction. So I'm going to take air here at N1, and I'm going to take water here as my example at N2, and we know that N2 is greater than N1. When you have a ray of light that goes straight up, perpendicular to the surface, then it doesn't bend at all. Because if you're going to get from this point to this point, your quickest path is going to be the straight line. So that's one way to think of it. And then if you think about the wave fronts, it does slow down, but they all slow down at exactly the same time. So even though these parallel lines get closer together, there is no bending involved. But if I go at a certain angle, I'm going to bend away from the normal. So if this is my normal, my theta 1 will be greater than theta 2. All these angles are measured with respect to that normal. And if I go at even a deeper angle, it's going to bend even further away from the normal. And there's going to be that limiting point at which it'll bend and skim the surface. Oh, by the way, as a lot of this light will refract and bend, some of it will still reflect, and that'll follow the law of reflection. So a portion of this light will reflect back under the water, and a portion of it will go out. When it's going straight, most of it is going to go out into the air. When it is going at this angle, the majority of it is going to go out in the air, and a little bit of it will bend back into the water. And when you get to this critical angle part, the reflection is going to increase, so there's going to be more reflecting, and then there would be some that will skim the surface. So the refracted part is going to skim the surface. So this is my theta 2. This will also be theta 2 according to the law of reflection. And theta 1 in this case is 90 degrees. We'll come back to that in just a second. But if my incident angle is bigger than this theta critical, so let me, instead of theta 2, I'm going to call this theta critical. That's the critical angle at which refraction skims the surface. And if my incident ray is bigger than that, then all of the ray will reflect and none of it will refract, because you can't have an angle bigger than 90 degrees for refraction. You can see that from Snell's law. So if I have n1 sine theta 1 equals n2 sine theta 2, you know that the maximum value sine theta can get is 1. Sine theta ranges between -1 to +1, but for the angles between 0 and 90, it ranges from 0 to 1. And so the maximum you can get with the sine theta factor is going to be just 1. So if I set this theta 1 to 90 degrees, it'll be n1 times sine of 90 degrees would be equal to n2 times sine of theta c, because this is the critical angle condition. And rearranging the sine of 90 is just 1. So I'll get theta c is sine inverse of n1 over n2. So whenever you have two mediums, if you know their indices of refraction, you can just get the sine inverse of the lower index of refraction divided by the bigger index of refraction, and that'll give you a certain angle. And if theta is less than theta c, then you're going to get refraction and some reflection. And if you have theta incident greater than theta c, you will have no refraction and all reflection. So this is called total internal reflection. And when you have a fiber optic cable, if you guys have gig speed internet, you could get it from Comcast, which is a cable. If you get it from AT&T, or I think even Verizon now, it's a fiber internet. And when they say fiber internet, they mean fiberglass. So what they do is they create a glass pipe where the index of refraction of the glass edge is smaller than that of the material that fills the gap in between. And so when they shoot a ray of light, it's going to totally internally reflect and get to where it needs to get to from point A to point B. So they can have light essentially bending along the cable because it's all being totally internally reflected. All right, so in this video, we looked at the refraction of light. We looked at why light rays bend when they go from one medium to another. We saw that they will bend toward the normal when they go to a medium of higher index of refraction and bend away from the normal when going to a medium of lower index of refraction. All of that was also encapsulated by this Snell's law, n1 sine theta 1 equals n2 sine theta 2, which then led to this critical angle conversation, which let us cover this concept of total internal reflection. Thank you.